Today's lesson is on the rotation of rigid bodies. A rigid body is an extended body whose size and shape does not change as it moves. And when a rigid body moves, it can either undergo translational motion, rotational motion, or a combination of both. So I'll start off with the definition. To understand rigid body motion, let's do a brief review of rotational motion. Consider first a disk rotating about an axis. So we can consider the disk to be this, and it rotates about a fixed axis with an angular velocity omega. If we take a point in this disk, we can look at an angle delta theta in that region, and this will be the angle of that region. If you extend this point over here, you can see that this region also has the same angle, delta theta. So this tells us that we can find the angular velocity omega, and this should equal the angular displacement with respect to time, the theta dt. This tells us that every point in the disk has the same angular velocity. If the disk is speeding up or slowing down, then we can calculate angular acceleration as follows. So the angular acceleration is a change in the angular velocity with respect to time. So let's look next at the rotation about a center of mass. When an object rotates freely, it rotates about a point called the center of mass. We can find the center of mass of a rigid body by first putting the rigid body in a Cartesian coordinate system, and then we shall identify points in the rigid body as little point elements as follows. Consider the rigid body below. Let's first draw an arbitrary shaped object on the coordinate system y and x. And let's first identify a point in this object which we call the center of mass. This will be at position xcm and ycm. Since we are saying this object is made up of individual particles, let's identify an element in this object which has a mass m subscript I, and it's at a certain position xi, and this position is yi. So we can imagine taking the sum of all individual elements in this rigid body and adding them all up to get the total location of the center of mass multiplied by the mass of this object. So we can define the x-coordinate of the center of mass of this object to be equal to the sum of the ith element, or the sum of one element at position 1 plus a second element at position 2, all the way to a total of n elements at position, the nth element at position n. And then we divide that by the sum of all the elements again. This can be written for the x component of the center of mass as the sum from I going from 1 to n, m subscript I, x subscript I, divided by the sum of all the elements m subscript I from 1 to n, and this gives us again the sum as I goes from 1 to n, mi xi divided by the total mass of the rigid body. We can do the same for the y coordinate of the center of mass by identifying again the same number of elements, the same number of individual elements, and adding them all up. So for the y center of mass, we have the sum as I goes from 1 to n of mi yi divided by the total mass. So for a two-dimensional object, the location of the center of mass can be found by using the formula above or by using the formula given. Let's look at a quick example of how we would use this formula. Let's consider an example from your textbook. This is example 12.1 in your textbook. A 500-gram ball and a 2 kilogram ball are connected connected by a massless 50 centimeter long rod. Let's find the location of the center of mass and the speed of the balls as they rotate about the center of mass. So let's first draw a diagram. So we have our ball. Let's put the first ball on the axis at the reference point, and the second ball somewhere here. And let's identify a location which we shall call the center of mass. So let's say the center of mass is somewhere here. So this is our 2 kilogram ball, and this is a 0.5 kilogram ball. The distance between them, we said, was 50 centimeters. So we can say that this distance, let's call it R1, and this distance is called R2. So to find the location of the X center of mass, we use the formula sum as I goes from 1 to n, mi xi divided by total mass. Since we are only in one dimension, we are just considering the X center of mass. And there are two balls, so we have m, so I goes from 1 to 2. So we can say that X center of mass is equal to the sum as I goes from 1 to 2 mi xi divided by total mass m. And so we can say this can be written as m1 plus m2 x2 divided by the total mass, which is 2.5 kilograms. Let's do it this way. Let's write it out explicitly first. m1 plus m2. So X center of mass can be written as m1 is your first mass. This is 2 kilograms multiplied by 0, since it's at the reference point, plus 0.5 kilograms multiplied by this is 0.5 centimeters, 0.5 meters, since it's 50 centimeters. Divide that by 2 plus 0.5, and that should give us 0.5 kilograms times 0.5 meters divided by 2.5 kilograms. So the location of the X center of mass can be written as 0.25 kilograms meters divided by 2.5 kilograms. This is equal to 0.1 meters. So the location of the center of mass is the 10 centimeter location along the rod. Now the second question is to find the rotation of each ball about the center of mass. So this is number 2. Each ball rotates about the center of mass. So if you draw a picture again, what you have here is this is your second ball. This is the center of mass, cm over here. This distance we said was 10 centimeters, which means that this distance is 40 centimeters. Remember that the whole rod is 50 centimeters long. So we can find the angular velocity. Let's first change the angular velocity to radians per second. So we have 40 revolutions per minute. So 40 RPMs. 40 RPMs is equal to 40 revs per minute. So we can convert that to radians per second. So we have 40 times 2 pi radians per revolution times 60 seconds per minute. And then we have revolution, of course. So the revolutions cancel. So we can cancel those, and that gives us our revolutions. That gives us the angular velocity in radians per second. So 40 revolutions, or 40 RPMs, is equal to 4.19 radians per second, or you can write 4.19 per second. Since the radian is not a true unit, you can leave out the word radian and just write 4.19 per second. That should also be fine. So now we can find the speed of each ball about the center of mass. So the speed of ball 1 is equal to r omega, so it's r1 omega. Speed of ball 2 is equal to r2 omega. So ball 1 is equal to 0.10 meters times 4.19 radians per second, which gives us 0.4, which gives us 0.42 meters per second. In the same way, we have 0.40 meters times 4.19 radians per second, which gives us 1.68 meters per second. So we can illustrate that the following way. Suppose we have this object, this is the center of mass, and we assume that it's rotating about the center of mass. So we'll have this object rotating with a speed v2, and this is moving with a speed v1. This distance is r1, and that distance is r2. So we found the center of mass to be this location. So this is the axis about which the object rotates. And it rotates, each object rotates with the speeds that are shown there. The whole setup is rotating at an angular velocity omega. So this works very well when you have two masses, but what happens when we have a distributed rod which is not made up of individual masses? In that situation, we can borrow from calculus, and we'll see how we do that next. So let me put down the question: how do we find center of mass for a distributed object? Let's consider the arbitrary mass we used earlier. So we'll draw again our coordinate system, x, this is y, and we have an arbitrary shaped mass in this coordinate system. So in order to find the center of mass of this object, let's take an element in this object of mass m subscript I, and its location will be x subscript I and y subscript I. So we found earlier the x center of mass for this object is given by 1 over m, sum as I goes from 1 to n, mi, xi. Suppose we say the mass is an element given by, suppose we say the mass is an element delta m. So we say m subscript I is an element of mass delta mi. Then we can have, for the x center of mass, we have 1 over m, sum over I from 1 to n, xi and delta mi. And for y center of mass, we have 1 over m, which is the total mass, sum as I goes from 1 to n, yi delta m for this mass. I think we can keep out the I subscript. We don't really need the I subscript there, because we are saying that all the elements have the same mass. So we just use delta m. So in order to sum all these elements in the mass, we can use calculus, and to do so we can imagine that we take the smallest element, so we continue dividing the mass element into tiny elements until we have a continuous, until we have a very tiny mesh of mass elements, and then we add them all together. This is essentially what we do in calculus when we do an integral. So we can think of taking the tiniest mesh, which means that we're taking the limit as delta m approaches 0 of the sum of all these elements xi delta m, and this just gives us the integral of x dm, and then we have 1 over m, of course, like that. And we do the same for the y component. This is the same as writing it this way. We take the delta m to be as small as possible, meaning that we are making the mesh very fine, and the mesh that I'm referring to is shown below. So if I draw this again, this is x, that's y, and we have some arbitrary shaped mass. If I take an element here, delta m, this element is at xi, yi. This is essentially dividing this into small element or small regions here, and we can take each of these as small as we want it. So this is the mesh I'm referring to. So the smaller the mesh, the better the approximation, and we can, instead of adding each individual element, do an integral to get a complete and accurate picture of what the center of mass should be. Let's see how this works in an example. This is the center of mass of a uniform rod of length L and mass M. So let's consider the uniform rod as shown below. This is going to be placed on the x-axis. So this is x and that's y. So we can think of taking an element dm, so an element of mass dm in this rod, and that element has length dx and is located at a distance x from the reference point or from the zero axis. Since the rod is uniform, we can say the density of the rod is equal to the mass per unit length of the rod. And so an element dm in the rod will have the same density if we take the dm divided by its length dx. So from there we can say that the element dm is equal to m over L dx. This is what we shall use as a substitution in our integral. So from our formula above, we know that x center of mass is equal to 1 over m, the integral of x dm. So we can say this is equal to 1 over m, and then we are integrating over the entire length of the rod. And so let's go from 0 to L, and this is x, and then we replace dm by m over L dx. So x center of mass can be found by integrating 0 to L x over L dx, which then gives us 1 over 2. This is x squared, 0 to L. So this can be written as L squared over 2L minus 0, which can then be written as L over 2. So for uniform rod, the center of mass of the rod is just halfway along the rod or halfway up the rod. So this tells us the center of mass is at the middle of a uniform rod.